Hi, I'm Ken Miller.
And I'm David Erdos.
And welcome to the Erdos Miller New Technology Podcast, where we spend our non-productive time talking about everything drilling tech. Big disclaimer for today, we're doing something a little bit different today. We are going to talk about concepts and educational high-level stuff, but we're going to use our products to demonstrate how that works, right? And so, we will be doing some shameless plugs today. So our podcast content in the past has been entirely educational.
Yes.
If you do not want to hear any amount of plugging, even if it's very low key at all, please get off the bus right now. If not, we will be going forward to our destination, right? I have a shout out. I have a good friend of mine, Mr. Mark Miller at Legacy Directional. Great guy. If you know him, make sure he hears this and gets this message through the podcast. But, sir, I have read your suggestions on LinkedIn, and they are not helpful. Thank you. Now we can continue.
I'll need to look up the context on that.
He'll get the joke. All right, so, Dave, today we want to talk about encoding or telemetry encoding and telemetry compression, right? And we can just drop the telemetry in front of both words and just say encoding and compression, right? Yep. And so what the hell is the difference? Explain it like I'm 5, like on Reddit, right?
Yeah.
Okay, I'm a 5-year-old. Explain to me the difference between encoding and compression.
Okay, so my data is, let's say my data is 1010. Encoding is saying I'm going to represent a 1 as a red dot and a 0 as a blue dot.
If I wanted to, I could take a blue pen and a red pen, and I could take a piece of paper, and I could draw blue, blue, red, red. 4 dots, right? Blue dot, red dot, and that would mean in binary 0011, right?
Yes.
Okay. And so I could go blue, red, I could go red, red, whatever pattern I wanted to, right?
Yeah.
And I could fill that whole sheet up with, blue and red dots from left to right, top to bottom, right?
Yes.
And I would have stored binary information to a piece of paper.
Yes.
Right? That's a great idea. That's a great example. It's a great analogy, right? And if I wanted to, I could create that document. I could store it in a file cabinet if I wanted. I could have, that stored for a long time, right?
Yeah.
And then I could pull it back out and I could re-decode it by hand, right?
Yes.
And then I could make a computer that takes a picture of it and then, finds the red and the blue dots and pulls out the data itself, right?
Yes.
So if I wanted to, paper with blue and red dots could be my data storage and transfer mechanism, right?
Yes.
Okay. So that's awesome. And like if I wanted to make something that lasted longer than paper, if I really wanted to, I could maybe say put indents and outdents on concrete.
Yeah.
Right?
Yeah.
And that could store data for like a long time, right? Like like millennia, right?
Yes.
Potentially. Or I could machine a piece of metal, right? All sorts of cool things to encode data, right?
So in essence, we're changing the representation of the data.
When we're taking it from this abstract concept of ones and zeros in our head or in a computer's memory, and we're taking it from there and putting it into something physical, right?
Yeah.
And so, like on an NVD system, if we get back to the practical reality, we're taking the virtual ones and zeros in the memory of the NVD system, right? And then we're putting it in the mud, and then we're pulling it back out.
And in the case of mud pulse telemetry, the encoding is in the timing.
Okay, so I can't. Piece of paper, I've got like a big area to draw on, right? But a mud pulse signal is essentially one-dimensional, instantaneously and two-dimensional over time, right?
Yes.
Because I have a time-varying pressure waveform, right?
Yes.
So can I just make a pulse if there's a 1 and have no pulse if there's a 0?
You can,
but
there's a lot of reasons you wouldn't want to.
I could feel the butt coming, so it's like tell me a reason I wouldn't.
So that would mean that your for example your power usage and first of all, let's talk about mud flow. So the mud flow needs to keep flowing for the motor to turn and to wash the cuttings up.
If I had a pulsar that completely shut off the flow, and not most of them don't, but if I did, that would be bad, because if I had the data stream of like 1 1 1 1 1 1 1 1 1 1 1 1, I might close the valve for a long time and then never open it again, right? Okay, but I could do like a something where I have like a bit and then a space and then open and close, but that space would always be there, right?
Yeah, and then that would take up more time.
So in that case, I actually have to what I'm doing at that point is my initial proposal for an encoding to work with mud pulse decoding, mud pulse telemetry was unsuccessful, right? If I just do just binary slot after slot after slot, it's not going to work, right? For different hydraulic reasons.
Yeah.
But I am now making, necessity is the mother of all invention, right?
Yeah.
And so now I'm thinking of a way, okay, now how could I make this work with mud pulse, right? So what I could do is I could have a data slot and then a rest, right?
Yeah.
And the data slot could either be high or low based upon the bit value, and then I could have a rest, right?
Yep.
And that would work because that wouldn't stop the flow permanently, right?
Yes.
Now, would that be as reliable? Because it might be hard to differentiate as to whether there's a pulse there or not, right?
Yeah.
It's also kind of inefficient, right? Because like half of my time transmitting would just be spent resting, and resting doesn't transmit any data, right?
Yeah.
So that's not helpful, right?
Yeah.
So what else can I do?
Well, the another thing you could do is you can encode. You can like somehow synchronize, the surface and the downhole timing, and then you can have a slot, and if you put a pulse within the slot, it represents one value, a 1, 2, or 3, and if you put it in a different place, it represents like
So
4,
what I'm
5,
going to do
6.
now is instead of saying, okay, I have just one slot and it represents either a 0 or 1, what we might have is 4 slots, right? And so 4 slots would represent 2 to the power of the second, right? So 2 bits. If we have 2 bits in binary, it's 4 possible combinations.
Yep.
0, 1, 2, 3, or in binary 0, 0, 0, 1, 1, 0, 1, 1, right?
Yep.
And so if I wanted to represent the number 1 through 4, I could have 4 slots in a row, right?
Yeah.
And I could put the pulse in whichever slot corresponded to the number, right?
Yes.
And that would allow me to say that creates a 2-bit mud pulse packet, right?
Yeah.
Kind of roughly as we know it today, right?
Yes.
And then the only thing I do have to put that rest in there, right? Because if I have a 0 followed by a 3, I'd have that same problem of backing into each other.
Yeah.
And so I've still got to put that rest in there, right, to deal with the hydraulics. And so that gives us a good idea of like, how encoding works and how it's done on mud pulse today, right?
Yeah.
So how are we changing that, right? So we're moving away from that, right? Because we've been using this MRA protocol forever, right?
Yeah.
I'm really excited because we have a new feature in MicroPulse called Pulse Overdrive, right?
Yeah.
And so we've actually started to finally move away from that, right?
Yep.
So
yeah, we're really excited because we're decoupling. Previously, we had the data rate coupled directly to the pulse width.
Yep.
If you have a 1 second pulse width, you have about half a bit.
So the size of my pulses and the size of the slots are always the same, right?
Yeah.
Yep.
And so with Pulse Overdrive, we're decoupling, separating the pulse width from the data rate.
Right.
So you can run a 1 second pulse width, but get an effective data rate as if you were running a 0.8 second
All right.
pulse
And
width.
now that we're into the shameless self-promotion, I just have to add another disclaimer. Zach made me do it. So, feel free to message him on LinkedIn and say, Zach, you're ruining the podcast, whatever.
Yeah.
But keep going. Yeah.
Yeah. And so we can run with basically narrower or faster data rates at the same pulse width and get more data and less pulse aware and all the other benefits you get.
So I told customers you can look at Pulse Overdrive in 2 ways, right? Either you can stick with the same data rate you've got and you can make it more robust, right? And so if you're happy with like the data rate of a 0.5 pulse width and you want to make it more robust so you can drill deeper with the 0.5, you can just turn on overdrive and that'll make a wider pulse and that will make it more resilient to noise, right?
Yeah.
But the other way you can think about it is that you can also say, okay, if I'm pretty happy with how deep 0.5 can get me, I can also, say, okay, well, you know what? I'm going to run 0.375 with the 50% overdrive, and that's going to get me still about a 500 millisecond pulse, but I'll get more data, right? Yeah. And so...
And just to elaborate on what that means is, let's say your pulse is originally this wide for a 0.5 second pulse width in time, the time axis. If you make it 50% wider, but in the same position, that's what Pulse Overdrive effectively achieves.
Yep.
As we widen the pulse, but leave it in the same position.
So we're still able to use those smaller slots, right?
Yeah.
And so the slots get smaller and the rest get smaller, which means we have more pulses, right?
Yeah.
And the data is more finely encoded, which means we go faster.
Yes.
Right? More data, right?
Actual throughput increases for a given pulse width.
It's so funny to me that like I meet some people in this industry who are like, oh, we have all the data we need, don't give us any more. And some people are like, God darn it, make it go faster, right? And so, and I've also heard people tell me that like, oh, if we had wired pipe and we were running it at 1 million bits per second, then, or not 1 million, 100,000 bits per second or whatever, right? They'd say, well, that's all the data we'll ever need, right? And I think that's utterly baloney, because I think that we will, like, no matter how fast of a communication link you give us, we will always max it out and then start complaining for more.
Yeah, we'll find a way to fill it.
Yeah, I mean, it'll take a little while, right? It'll take a few years to fill it up and make sure we get everything useful and figure out what's truly useful or not, and then we'll start compressing what we can.
Yeah.
And then after that's done, we'll go, crap, I need more raw bandwidth, right?
Yeah.
All right, well, today's kind of a big podcast with 2 big concepts where we're going to put a little bit of break in the middle, right? And so Tom Petty was always one of my favorite artists, and so one of the most hilarious things he did was even on his CDs, he put a break that the CD listeners had to listen to in fairness to the people who were buying the LPs.
Right, just flip over the record.
Yeah. So, our podcast is brought to you by Micropulse and Eclipse Touch, our products. And if no one buys them, then we can't do a podcast.
That would be sad.
So thank you all for buying our products and listening. And, thanks for tuning in. And so that brings us to the next topic, which is, so I think we talked about it and gave a really good analogy for encoding. Let's talk about compression now, right? What is compression?
Yeah, I mean, I think we're all familiar with like zip files.
I don't think we should make that assumption.
No? Okay.
Everyone knows what a zip file is. I don't think anyone knows most people don't know how they work.
Right.
So let's talk about that.
Okay. Compression is we take data and we make it smaller.
How do you magically make it smaller? Because like if I have a book and it has all the words in the book, how can I just make it smaller? Because it's going to take up so many pages, right? Am I just like writing it smaller?
I mean, that would be one way. That would be a physical compression.
I wish you had said no, because I that's not going to work for my analogy.
Okay, no. Then we'll say no.
We'll say no, right? Because I need that. I can't change the font size.
Yeah.
I can't change the font size. How do you make the book smaller if I can't change the font size?
So one common technique is you can make like a dictionary for that specific book.
Yep.
So, some obvious things. If there are empty pages in the book, you remove the empty pages and just say there was one empty page here.
Okay, and you can put that back in, right?
Yeah, and then you just put that back in.
It's like finding a simpler way to explain the data, right?
Yeah, and you find like patterns in the data and represent those patterns with a smaller representation.
So let's say that that the book just contained regular English words and then regular English pronunciation, right?
Yeah.
And so let's say it didn't contain a character like a carrot.
Yeah.
Right? And so what we could do, for example, is when you say make a dictionary, is we could say, all right, well, I'm going to go through the whole book and I'm going to find the word the.
Yeah.
And I'm going to replace the word the with the up caret, right?
Yeah.
And that would take 3 characters and reduce it to 1.
Yeah.
And that would give me a 66% compression, right? And in the dictionary would say up caret is equal to the word the, right?
Yeah.
And so in the process of compressing, what I would do is I would go and rewrite the book, and I would replace the word the with the up caret.
Yeah.
And then I would go and when I went to unpack it and uncompress it later, I would go back through and say, oh, okay, every time I find the up caret, I'm going to replace it with the word the, right? And that would make the book smaller in the process of doing that, right?
Yeah.
Now, I might have to do that for a lot of different words.
Yeah.
Because that probably alone wouldn't give me a good compression ratio overall.
Yeah.
But that's the basic idea, right?
Yeah, and some things are going to be more compressible than others.
Okay.
Like if your book has 100,000 occurrences of the, it's going to be more compressible than if it only has one in your example, or if like there's no repeated words. Well,
a novel might not be highly compressible because every sentence is pretty unique, right? So the most you could do is like maybe compress the common English words, right?
Yeah.
But let's say that you had some spreadsheet data, right?
Yeah.
And that spreadsheet data had a lot of the same patterns in it, right?
Yeah.
So the bigger, more common patterns that you can find, the better that you can compress data, right?
Yeah.
And so what this allows us to do is, so this is the zip file analogy, and in a minute we're going to tell you that everything we have to do in MudPulse is entirely different.
Yeah.
But so the zip file analogy is I could compress the data, right? And what that gives me is the compressed file plus the dictionary.
Yeah.
And then I transmit that over my data link.
Yeah.
Right, which is in most cases the internet.
Yes.
And on the other side, there's a decompression program that looks at the dictionary and the compressed data and unpacks it again.
Yep.
Right. So I mean, it's kind of like I'm not even gonna say it. Well, I'm just gonna finish it now. But it's kind of like putting all your clothes in like little vacuum bags and then unpacking. Putting the suitcase, and getting in the airline and unpacking it. Not really though.
Because you're removing the air. You're removing the excess.
All right.
Material.
It's not the best analogy.
Yeah.
I'll allow it. Right.
Yeah.
Well, but can I always? So here's a question. Can I always be guaranteed that if I compress the book and then send it across the wire, that I get the same book on the other side?
That depends. Depends on your compression technique.
Okay, well, tell me about that.
In the compression techniques we've talked about, yes.
Okay, so these would be what's known as a lossless compression, right?
Yes.
Meaning nothing is lost during the compression process, right? So by corollary, what is a lossy compression, right?
Yeah, so virtually every image representation on a computer is a lossy compression.
Okay.
So like JPEG is a lossy compression.
So I take a really high res picture with my phone or my camera, or my phone and my camera, because they're all high res now, right? And then that takes up a lot of megabytes, sometimes gigabytes, right? But we probably don't need all that resolution, right?
Right.
And so if I want to share that picture on the internet, I'm not going to put up the original raw file that was a gigabyte. What do I do?
Yeah. So you would then compress it with another lossy compression, which like a JPEG. And so that's going to take commonalities in the image data and replace them similarly to how we described the dictionary, except it's not going to be a perfect representation. You might have, one pattern that's very similar to another pattern, and you'll say, they're close enough. We'll replace it with the same key in the dictionary.
Gotcha.
And so to the eye, you might not notice that you probably can't tell an uncompressed versus compressed, depending on
this was
how fine you
the brilliance
compress
of the MP3, right? So with a lossy compression, what you're saying is, in order to get a better compression ratio, I am willing to toss some data out.
Yeah.
Right now, with my quarterly financial reports, I probably don't want to do that.
No.
I probably
or
don't
your
want to.
firmware.
I probably don't want to zip up my quarterly financial report, send it to my boss, and then have him unpack it and have him get something other than exactly what I sent him.
Yeah.
Right. So that only a lossless compression would be appropriate for that,
Yes.
like a zip file, right?
Yeah.
But with an image, we can pretty much show almost the same exact image to the human eye.
Yeah.
While throwing out a bunch of data, right?
Yeah, and
save
you
a
wouldn't
lot,
lose
right?
you wouldn't lose any of the meaning of the image. It would still be an image of a house.
Yes.
Just like if you look very closely, maybe some of the edges have a little bit
Like
different.
zoom way in on the pixels or something like that.
Like
right?
1% different pixel color.
But you might have a 100 megabyte image that becomes 1 megabyte with these lossless compressions,
Yeah,
right?
it's huge savings.
Yeah, with anything that a human perceives like that doesn't need to be exact, you can get crazy amounts of compression, right? Now, another classic computer history example of that is the MP3, right?
Yeah.
Because the MP3 took all the wave audio format is incredibly high resolution, right?
Yeah, it's lossless.
It's lossless. But if you cut out all the frequencies you can't hear, you can save, like literally that the human ear can't hear, you can save a ton of data and take a 600 megabyte song and turn it into a 3.5 megabyte MP3, right? And that was the big innovation with the MP3. Remember that correctly? Or? Yeah. Okay, so this was important to teach everybody about the basics of industry standard compression concepts,
lossy
right?
versus lossless.
So we can't apply any of this downhole, right?
Unfortunately, no.
Totally useless.
Yeah.
Well, not. I mean, with higher res LWD data, we can apply some of that, right?
Yeah.
But like
gamma resistivity images,
most stuff we can't, right? So anyways, we just came out with a survey compression feature on the MicroPulse, right? So let's talk about how that works, right? If we can't use loss, like a zip file lossless compression, right? And lossy would not be acceptable for surveys, right? Surveys have to be exact, as precise as possible. Then how the heck do we compress that?
Well, should we start with disclaimer?
Disclaimer, yeah.
Disclaimer, our survey compression techniques are patented.
Right, so there you go, right?
Pulse overdrive is patent pending.
Yeah, so...
FYI.
Yeah, okay, so we can talk about it because the ideas in it are pretty securely protected by the patent, right?
Right.
Okay, well, maybe that was a reason to get off the bus, but whatever. Okay, so yeah, go ahead.
So... in much the same way that we talked about compression earlier, we take something that we know.
Yep.
Like we know the word "the" is going to appear multiple times in a novel.
Yep.
We take things that we know about, virtually all directional wells in the U.S. is there's a vertical portion, there's a curve, there's a lateral.
Yep.
In the vertical, you're only going to be within a very small range of inclination. Your azimuth's kind of undefined. And you have different parameters, your qualifiers, total gravity, magnetic field, dip angle, all should be within nominal. And so we can take all these knowns and we can kind of hone in and say, okay, if we're in the vertical, our inclination's not going to change more than 5 degrees, and so we can basically strip out the extra bits.
It shouldn't change more than 5 degrees.
Shouldn't change,
right?
and if they do, we just fall back to uncompressed.
Yep.
But we know.
Well, can I say that another way, right? So if we're drilling a lateral north, right?
Yeah.
And so I'm going to drill down vertical, curve, lateral. If I drill out north, there is no way in heck that tool is going to tell me that all of a sudden it's going south, right?
Right.
Like it is physically impossible for the borehole survey to survey to just loop around and go the wrong direction, right? I mean, now if you're drilling a horizontal, if horizontals become common, this is not going to work.
Yeah.
But it would work okay.
We'll come up with a different technique for that.
It would work okay. But anyways, so the fact that we know that we're going to drill a lateral, it's going to go north, and that there's almost no chance for the tool to tell us south, right?
Yeah.
It really should be about plus or minus 10 degrees around north, right?
Yeah.
And so what we can do is we can say, okay, there's a bunch of information here that I can just throw out, right? And the tool doesn't need to have the ability to tell me if I'm going east, west, or south most of the time because I'm going north.
Yeah.
Right. And so what I can do is I can take that same precision that we need and restrict it to just being around plus or minus 10 degrees north. And I can save a ton of data and I can get the real information I need even faster. Right.
Yeah.
And so we compress surveys. It's lossless compression, right? Not lossy, right? But what we did is we looked on the outside for a pattern and not the inside for a pattern, right? We didn't look within the data and try to discover patterns. We looked at the drilling, the drilling practices and discovered a pattern in those, right? And then bake that into the technology, right? So we're still taking advantage of the fact that there's a pattern, right?
Yeah.
But it's not, just by looking within the data for, compressible repeating patterns, right?
Yeah, we're not saying inclination was 90 degrees last survey, so we'll assume it's going to be 90 degrees this next survey.
That wouldn't work for like a myriad of reasons, right?
Yeah.
But and so surveys are like 54 bits, right? Or 55 bits. Like there's just not a lot of bits in a survey, right? So like when we're talking about compressing like quarterly reports or Shakespearean works or whatever, we're talking about either kilobytes, thousands of bytes, or millions of bytes of information, right? There's plenty of data in there to look for patterns.
Yeah.
But like 55 bits.
Not a lot of patterns.
Not a lot of room to have a pattern, right?
Yeah.
And so that's how that works, right?
Yeah, and so kind of akin to our earlier analogy, there is still a dictionary, if you will, in that the tool knows ahead of time what azimuth it's going to be drilling at and what the known inclinations are. So that's kind of the common dictionary.
Yeah, because we tell the tool it's supposed to be going north, right?
Yeah.
Right. And so what happens if all of a sudden we actually do go east because someone made a big boo-boo, right? Like what do you do?
Yeah, so then we just, switch back to sending back the full uncompressed telemetry sequence, which can represent all angles and all measurements fully.
Yep.
And so
it's a fail-safe, right?
Yeah, it's a fail-safe.
So we can just go back to sending the full range, everything we need to, like old school, right?
Yeah.
And guarantee that you always get accurate information either way. But like when you're going the way you're supposed to, we can go really fast.
Yeah.
Yeah.
And so on the topic of speed, like, any of these techniques in isolation, pulse overdrive, or just survey compression by itself, you might get like 30, 40, 50% savings. But when you start stacking them on top of each other, small gains really start to add up.
Oh, yeah.
And you get significant time savings.
Two-thirds, gains stacked on top of each other are over 50%, right?
Yeah.
So when you can cut the time of surveying in half, that's pretty cool, right?
Yeah.
So, awesome. Okay, well, I think thus ends our shameless plug, and but backed up with a little bit of education about compression and encoding techniques. I love the red dot blue dot example. That was a really good one you came up with. So.
Yeah, I'm glad it worked. Coming up on
keep
the spot.
that one for teaching your children about encoding, right?
Well, that's all the time we have for today. I'm David Erdos,
and I'm Ken Miller.
For any new listeners, please be sure to check us out on iTunes, Spotify, and YouTube. Like and subscribe. Thank you.
Thank you.